Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Gregg and Paul Wiegert with us today. Hello, Cole. Hello, Paul.
Hello,
Hello,
everyone.
thanks for having us.
And Paul, let's start with you. What's your geolocation?
I am in London, the other London, London, Canada. Enjoying some beautiful spring weather. Well,
Ah,
spring anyway for Canada. So,
very good. And Greg, you are in the same?
Yes, I'm also in London. Yeah, we're at the University of Western Ontario. Like Paul said, we got a hint of spring here, but then we woke up to a dusting of snow. So,
Ah,
right.
So I mean, let's see, it is March 26th of 2025 as we record this, and I'm in Phoenix, and we got very close to our first triple digit Fs the other day. So we got up to about 97 or so 38C or something to that effect. It was toasty, and we definitely don't get any snow. So, and Cole, what's your position there in Ontario?
I am a PhD student under Paul. I'm in my fourth year now.
Well, let me be perhaps the first to wish you a very early Dr. Greg.
Thanks.
It'll be very cool. Let's see. And Paul, what do you like to do for research?
so my research is concentrated on the solar system primarily, asteroids, comets, the smaller bodies, meteor streams, and so forth.
Oh,
And recently becoming more interested in that kind of material being delivered from outside our solar system. Very exciting sort of new development in the field.
absolutely. And Cole, what do you like to do for research?
I have a lot of similar interests to Paul. That's why I think it's been great to have him as a supervisor. But yeah, small bodies in the solar system dynamics has always been a big interest to me, as well as surveys for near Earth asteroids and so on. But I've always had quite an interest in interstellar material, just the very interesting applications of material from other star systems coming here and what that means. So that's a big interest of mine.
Awesome. I'm going to predict a very, very cool PhD thesis. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A case study of interstellar material delivery, Alpha Centauri, and Cole and Paul. Take us away.
Okay, yeah. So this paper is really about just trying to investigate the possibility of a dynamical pathway from another star system to the solar system and that delivery of material. So naturally, for the first case study, we kind of chose the nearest star system to us, Alpha Centauri. It's a very interesting star system,
Mhm.
and sort of the easiest place to start because perhaps that short distance allows that material to be delivered possibly more efficiently than other star systems.
Okay.
So that's where we started. And the reason why is because there's a lot of new interest, I suppose, in interstellar material because of the recent discoveries of Oumuamua and Borisov.
Hmm.
So these two large macroscopic interstellar bodies sort of resparked that interest in material being delivered from other star systems, though it's been a long standing sort of question when it comes to smaller bodies, especially. We have evidence of interstellar dust in the solar system, and there's been a lot of talk about interstellar meteors in the atmosphere of Earth. So that's why a lot of this interest sort of begins. And what we wanted to do here is we wanted to look at the relatively recent past, astronomically speaking. So the past 100 million years of Alpha Centauri potentially losing material into the galactic potential and seeing whether or not that material could make its way to the solar system.
Okay.
So naturally, the first question in this would be, does Alpha Centauri lose material? Could it be directing material into the galactic potential?
Hmm.
So that sort of is the first place to start, and we can kind of say, well, if it's an analog to the solar system, we know the solar system could be losing material because comets could be coming in from the Oort cloud. They can have a gravitational perturbation from, say, Jupiter and get kicked out entirely. So that's sort of the first place to start. And it's a very similar system in the sense of the masses of these stars are very sun-like.
Mhm.
So we could, and there's a binary for the Alpha Centauri A and B system. So we have that mass that could be there, that could be lost. It could be retained in those asteroid belts, Kuiper belt, or cloud type reservoirs.
Cool.
And these perturbations from the binary system, as well as the triple with Proxima Centauri, could cause these ejections to occur and
Yeah.
material to leave the system.
Yes, I'm with you.
Perfect.
I'll jump in here and add that so we don't know if Alpha Centauri has planets. Well, there is one confirmed planet, but there have been a few other reported planets.
Yes.
There could be other planetary bodies stirring up the mix and adding to the ejection processes. It's really a fascinating topic, whether, what exactly is going on inside this complicated triple system. It's so close to us, and yet we still don't understand the structure very well. But I think it's very, very plausible that it is ejecting material. I mean, our own solar system does it, and our solar system is less dynamically complicated. So
Yes.
I think it's a reasonable assumption that Alpha Centauri is ejecting material, but can it get here? So that's the next part of the question.
Right.
Yeah. So if you scroll down, hit these are some points we have in here about what makes Alpha Centauri interesting, and I think
Okay.
what we just mentioned, we kind of covered a lot of it. So the big thing here is that we don't simulate the actual system and whether or not it does eject material. Instead, we assume that, and then we adopt a ejection velocity distribution from the research. So we do that from a Baylor-Jones AL paper in 2018.
Okay.
So we will get to that point, but just to summarize a little bit of the system itself, it's written here. We have a binary system, Alpha Centauri A and B, which is about solar masses, and then we have that brown dwarf Proxima Centauri that's orbiting around that binary system to make it a triple star system.
Yes.
Just some interesting points about the star system itself.
Okay.
And then with that, I think we can probably jump over to our methods now. And so how we run these. Oh, sorry. Yeah, I can make that point about
Yeah, I thought that was
about 28,000 years.
yeah.
So that's another interesting aspect of the system is that it's coming towards the solar system right now. It's having its closest approach in the future, which means any material that might be leaving the system, kind of spreading out in a stream, is heading towards us,
Cool.
which allows that dynamical pathway for that material to get to us a bit more interesting, a bit more plausible.
Very good. Cool. Okay. Onwards to the methods.
Yes. So for the model of the galaxy, we adopt a fairly simple galactic model. We just take the overall in time-independent gravitational field. So this is from the Miyamoto and Nagay, the 1975 paper. So it's a three-component, time-independent, axisymmetric potential. So the three components are from the bulge, disk, and halo of the galaxy.
Yes.
Which summarized in equation 1 there. And if you want to know the actual details, equation 2 and 3 can
Yes.
put that to better situation. But the reason why we can do this, we can use this sort of overall potential, is because the time between stars actually causing an interaction with each other from getting actually close to one another is that relaxation time that's given just above there, 10 to the 7 billion years.
Yes.
So a very, very long time before stars actually gravitationally interact with one another.
Yes.
So that is why we can neglect those individual gravitational influences from each star.
Okay. Good.
So with that, we have our sort of potential, and we summarize these values of how we initialize the system right here in table 1. So we have the masses of the individual components and the position and velocity of the sun within it. And then we also have our Alpha Centauri positions in the Icarus frame.
Got it. Okay. Mm-hmm. Mm-hmm.
Yes, and
Okay.
Paul, anything you
Okay,
add
well,
to that?
maybe I'll jump in here and say a little bit about particle sizes. So one question, well, it's going to come up again a little bit later, but how, you know, what particle sizes do you expect to see delivered from Alpha Centauri to the solar system?
Okay.
So larger particles can survive the journey, but it turns out that smaller ones may actually have some difficulty surviving in the ISM. They can be eroded by different processes, and it's quite a well-developed subject of the understanding of dust in the interstellar medium, and we have just sort of adopted some of the literature values there. But it
Okay.
turns out that relatively small particles, well, maybe down to 100 microns or so, can survive the journey, but smaller particles might actually not be able to survive their time in the interstellar medium. So our
Right.
model, Cole's model, does a very good job of describing a wide range of particle sizes, down from small meteor in our atmosphere sized particles, all the way up through asteroid-sized Oumuamua, Borisov-sized particles. We've got quite a nice dynamic range in terms of masses there.
Cool. Very good. And roughly how many particles do you track?
We end up with just over 1 million overall. So we
Okay.
eject 10,000 particles every million years for our 110 million year simulation.
Okay.
So we attempt to keep a continuous ejection sort of going in the simulation and track all of them throughout that time.
Good.
So yeah, and we don't need to go over too much specifics here with the simulation, but we use an RKF method for the integrator.
Mhm.
We do that 110 million year integration starting 100 million years in the past. So first we just simulate Alpha Centauri and the Sun back 100 million years, and then we begin our simulation forward with the ejections as well. And that's when I mention here is the 10,000 particles representing the material from Alpha Centauri are added every 1 million years throughout the simulation.
Okay,
Uh,
cool.
and then a little bit back to the ejection model, like I mentioned earlier, we adopt an ejection speed distribution from the
Yes.
scattering of a binary star system. So that is from Baylor-Jones et al. 2018. They simulated a solar mass and a zero point 0.1 solar mass star system and how they might eject material. So it's not an exact match for the Alpha Centauri system, but gives an idea of that binary star system and how fast it might be ejecting material.
Right. And this is a isotopic ejection.
Yes, yes, yeah. So we use an isotropic ejection model. So we get those 10,000 random speeds from that distribution,
Yeah.
and we just apply them to random directions
Got it.
and implement them into the simulation.
Okay. Good. I'm
And
with you.
yeah, and then we just track them as the simulation continues. And if they encounter the solar system about within the Oort cloud, so we define a heliocentric bubble of about a radius of 100,000 AU.
Okay.
Uh, and if any of those particles come within that 100,000 AU distance of the sun, then we classify that as a close approach and say that that is entering the solar system.
Cool. Very good. Okay. I'm with you.
So with that, we pretty much just jump right into the results. So um, we
Mhm.
can see if you actually should go down to figure one, we
Yeah.
can see what the ejection velocity distribution actually was for all of the particles. So the right pane here, the cumulative distribution, is a recreation of that distribution from the Baylor-Jones et al. Paper, just to recreate it and show we're using that same distribution. And on the left is just a histogram of all of those ejection velocities. And you can see our median ejected velocity was about 6.5 kilometers per second.
Yep.
Mean 11.43, but it goes all the way up to over 80
Yeah.
kilometers per second for
Yeah.
that
Wow. Okay.
extent. Yeah.
Relative bullets. Okay.
Yes, yeah. So
Cool.
after we started the simulation, we let it run all the way through. We end up with a total of, like I said, just over 1 million total particles. So it was 1,090,000. total ejected particles, and of that, only 350 became close approaches with the solar system.
Okay. Okay.
Despite being a very small number in comparison, 0.03% of the total ejecta,
Yeah.
that still tells us that there is a dynamical pathway that exists that can deliver material from Alpha Centauri to the solar system, which I think is the main takeaway here, that that does exist. It is possible. Um, and
Yeah,
that
that's
was,
very cool. And I'll jump in here too, because I know Cole's going to say this, but the most of the particles that are arriving actually have relatively low ejection speeds. So between 1 and 2 kilometers per second from Alpha Sun, which is actually the more common speed. So lower mass planets or relatively lower mass bodies in the system will eject at lower speeds. So the
Well,
high speed tail that you see there
yeah.
on that figure is from encounters with the star.
Yeah.
Uh,
Scatter. Hmm.
so the lower speeds are the ones that we actually expect to be more common. You can see them highly represented there in that histogram, but that means that
Got it.
relatively low mass planets or other bodies in the system could be ejecting this material. It's not something that we would maybe have to, stretch our intuition in order to, believe that it's happening. It's actually something that we would be, we would really expect to be happening in the system, especially because there are confirmed and proposed planets there. So very exciting. It's very physically plausible.
Yeah, yeah, yeah. And so we get some low speeds. We know a distance, and yeah. Very good. Okay.
yeah,
Cool.
we can actually jump right to figure two now.
Sure.
So this is it's actually an animation. So this just shows all of these particles as they're being ejected throughout the time and how they evolve in the galactic potential.
Okay.
Uh,
Want to put the animation up now?
yeah, sure. Yeah, let's
Let's
see it.
let's go ahead and stop this share, and we will share the first one, which is this one. Okay.
So yeah, in this animation, the top row here is the galactic coordinates. So in the top left, we get X, Y positions, top right, Y, Z positions.
Okay. I'm with you.
So that's the galactic potential, and in the bottom row, those are relative positions to the Alpha Centauri system.
Okay.
And that's following a co-moving frame with the system. So the blue arrow is always pointing towards the galactic center, and the black arrow is in the direction of motion for the system.
Cool. I'm with you. Okay. And let's let it roll.
Okay, yeah, and the gold star there is Alpha Centauri. The black hexagon is the solar system. So we can see as this sort of progresses, we get this stream of material evolving in the galaxy.
Yeah.
Um, we'll glitch you in, and I'm not sure if it's totally clear, but those red points are actually the 350 particles that result in a close approach to the solar system.
Ah, very cool. Okay. Got
So
it.
we can see they actually sort of intersect with the black
Right there.
hexagon.
Yeah,
That's,
yeah. Right when, especially in this one, once they go through. Uh-huh.
yes, yeah. So that happens. Generally, the most of them happen when Alpha Centauri and the Sun are closest to each other, but not necessarily only when they're closest.
So this is going from 100,000 years in the past to current epoch, yeah?
Yeah, and it actually goes a bit beyond. It goes 10 million years in the future. But as we'll see, it's after about after around the closest approach to Alpha Centauri and the Sun,
Yes.
the closest approaches tend to end. We get this cutoff, and the rest of the simulation doesn't result in too many close approaches. We get some random ones up to a few million years in the future, though.
Oh, that's interesting. Okay, so it's sort of bursty.
Yes, yeah.
Okay, okay. Very cool. Okay, nice. Keep that in mind. You can go grab a copy of that animation for free, folks. So go get one. And let's go back to the article and boom. Okay.
Perfect. Yeah, and if you want to scroll back up just a little bit back
Sure.
in the paper. So with these close approaches, we get that there is, like Paul mentioned, the ejection speed distribution from planets is typically between 1 and 2 kilometers per second,
Okay.
and the 52% of our particles that arrive from Alpha Centauri as close approaches are actually less than 2 kilometers per second with their ejection speeds.
Wow.
So
Cool.
like Paul mentioned, the planetary ejection mechanism could be a large contribution to these
Yes.
particles that do result in close approaches.
Mm-hmm. Mm-hmm.
And then I will also mention that for the time that these particles were ejected that resulted in close approaches,
Yes.
they range from anywhere ejected from the system 93 million years ago up to just 12,000 years in the past. But that is heavily weighted towards the more recent ejections.
Okay.
So it is those relatively recent past ejections that are the higher concentration of the close approaches.
Okay. That makes some
Yeah,
intuitive.
that's an interesting fact that was a little bit, I guess it shouldn't have been unexpected, but it caught me a little bit by surprise. And that is that most of the material gets delivered in the relatively short time when Alpha Centauri is passing near us.
Yes.
And it makes sense when you think about it because our solar system has a much larger cross section. So, effectively we can catch more of that material when
Drive.
Alpha
Drives
Centauri
the
is
flux
closer.
up.
So
Yeah. Drives the flux up. Mm-hmm.
exactly, exactly. So, I mean, we do get older material that was, released in the past, but it does sort of increase as Alpha Centauri passes near us. So a lot of that material is sort of relatively fresh in that sense too, which is kind of exciting.
Yeah. Yeah. Very
And
cool.
this helps a lot, and we'll get to this a little bit more in the discussion. But when we talk about what size particles might survive, the less time they spend in the interstellar medium, the smaller they can be when they make it without other influences sort of perturbing their motion.
Mm-hmm. Mm-hmm.
Yes. Um, and then if we go up to the top row here on the right, we can talk about some other interesting implications with looking at the speeds of these particles as they're approaching the solar system.
Mm-hmm.
So we get the median apparent velocity relative to the sun is about 32.5 kilometers per second. So it's in the
Yeah.
leading up to this equation here.
Uh-huh.
The reason why that's interesting is because we can take that velocity, that relative velocity when it's outside the solar system, and then pull it into the solar system from the gravitational influence of the sun. And we can figure out what the heliocentric speed might be for these particles when they are in the inner solar system.
Okay.
So we can use this equation 4 here
Mhm.
um, with that relative velocity, that delta V, and we can convert it into a heliocentric velocity from that gravitational pull from the sun.
Yes.
Um, and with that, we get a range of 44 to 111 kilometers per second
Interesting. Yeah.
at 1 AU from the sun. So that would be how fast these objects might be moving once they're in the inner solar system, once
Mhm.
they're at 1 AU, so the Earth's distance from the sun. And the median of that is about 53 kilometers per second. So that's that speed we might sort of look for when we're looking for, say, perhaps a interstellar meteor in the atmosphere
Okay.
from Alpha Centauri. This would be perhaps the expected speed that it would have for heliocentric velocity.
Nice. Very nice. Okay. I'm with you.
Okay, and that leads to sort of meteor radiance.
Mm-hmm.
So that is uh, what on sky position these things might be sort of coming from when we're looking at them, when we're trying to find them, perhaps as an interstellar meteor. And we get that
Hmm.
the average position of them is fairly tightly clustered around what we call the effective radiant of Alpha Centauri. So that's just taking Alpha Centauri's velocity, sort of putting it in the opposite direction and converting that to an on-sky position. Um, so most of these particles are coming from that general direction with the effective radiant.
Okay.
But as Paul mentioned, with the effective cross section of the solar system sort of growing in size as Alpha Centauri gets closest,
Yep.
so does that radiant. So particles that are ejected more recently have a larger spread that could be on the sky for when they arrive
Yeah.
at the solar system.
Okay.
So that second position, sort of the second radiant spread, has a large plus minus 17 degrees
Yeah. Uh-huh.
rate ascension and 8 degrees in declination. But
Yeah.
uh,
Maybe
but
we could look at that figure. It's is that one of the later figures? I think it is.
yes,
Figure eight,
figure eight.
nine.
figure 8, figure 9.
Yeah, I think it's figure 8 or figure 9. So let's slide down and take a look at those. There's figure 8. That's your effective radiance.
Yeah, so the
Yes.
lower panel there, I think maybe is
Figure 9.
gives the best overall picture. So if you were looking for a meteor from Alpha Centauri, you'd actually expect to see it in the southern sky if it was going to arrive. So they're arriving from declinations which are quite far south. So we
Yeah.
were lucky enough to see one of these in the northern hemisphere, unfortunately. And as far as we're aware, none of them have been seen in the southern hemisphere either. But they
Okay.
have a very characteristic arrival direction. So
Yes.
if you did see a high speed meteor coming from that direction, that would be not necessarily confirmation, but it would be um, indicative or maybe diagnostic of meteors coming from that direction. So that's a direction we might want to look for them. But as Cole will tell us later, we don't expect these to be very common either. But that's where we would look for them. If they were arriving. So
Very cool. And you've got some of the more famous ones up here, which do show up in the northern, yeah.
Yes, yeah. We have a few potential interstellars and a couple confirmed with Umabo and Borisov, sort of plotted alongside these just to see if anything sort of correlates with what our potential Alpha Centauri particles might be coming from. And as you can see, none of them are smack down in the middle of where we expect this Alpha Centauri material to be coming from. So we don't believe anything that has been proposed so far would be a result of Alpha Centauri ejections.
Oh, you skeptic, you. Okay. Very good. So, yeah, of order million years, order magnitude-ish. Yes. Okay. Cool. Nice figure.
Thanks.
Yeah. Okay.
And actually, if you go to the one just above that as well, also with these radiant, you can see the left here is again just both those sort of those radiant positions, but on the right we zoom in to around the effective radiant of Alpha Centauri, and you can see that is where the majority of the material is sort of coming from is around that effective radiant of Alpha Centauri.
Got it. Got it. Okay. Q3.
Um,
There's that one, that one. And where's Alpha in there? It's the effective.
yes.
Okay. Cool.
Yeah.
Cool. I'm with you. Mm-hmm.
Okay. Yeah, and then if you want to sort of go down now into a bit of the discussion, I think that's where a lot of the interesting implications and we kind of get to.
Okay, so let's go. Section 3 is where we're at.
Yeah, we were just talking about some of the results here. Actually, if we want to show Figure 3, that is the animation of sort of the shower of interstellar material coming from Alpha Centauri into the solar system.
Okay, let me just orientate myself on the figure a sec. Okay, and let's go ahead and bring up that second animation with some degree of efficiency, I hope. Let's see, and this one.
Yeah, so this one is similar to that bottom row of that first animation, except it's co-moving with the solar system. So again, the blue arrow is always pointing towards the galactic center. Black arrow is following the sun's velocity.
Okay.
And then the gray shaded region is the Oort cloud, sort of in this frame.
Yeah.
And we can see these red particles again. Those are the close approaches, and we slow down near Alpha Centauri's closest approach, and we can see just the density of those particles passing through the solar system around that time.
And here we go, coming up. Slow down time.
Yeah. So, and this it kind of extends out quite a bit because we get a few
45, yeah.
after quite a few million years.
Yeah, that's what you're saying. There's a long tail that you'll pick up some at, millions of years later, but the bulk happens at closest approach.
Yeah, exactly.
All right, there was one. There was one, a real early one. Okay.
Yeah.
These are early ones or old ones, I guess I want to say.
Yeah.
Depends.
Yeah, and here's again around that closest approach time.
Very
So
nice. Very cool.
Yeah.
I get it. Very nice. Those are great. That really helps cement the visual in. So very cool.
Good.
Okay, let's pop back. So thanks for sharing those, and we will go back to the article. Bang.
Yeah, and then we have a few other figures here which kind of just show some of the statistics, I guess, of some of these close approaches. Um,
Yep.
this figure four here is the arrival times. So we sort of saw that in that animation.
Hmm.
There's a large peak around that closest approach of Alpha Centauri to the solar system, and it's just zoomed in a bit more on the right panel here. So we
Ah,
get the peak around that closest approach of Alpha Centauri, but we get this tail mostly around the plus minus 200,000 years of that closest approach, where we get the bulk of the material arriving. And this green line here,
yeah.
uh, that is, as Paul mentioned, the effective cross section of the solar system relative, like as the point of view from Alpha Centauri.
Hmm.
It
Hmm.
corresponds when you get the from Alpha Centauri, when you see the solar system as the largest, the most amount of material can actually be delivered because you can catch more, like as the same way
Right.
Paul kind of referred to it.
Gives the what gives the error bars on the histogram?
That is just a statistical with the number of particles that are in those bins.
Just sort of like a root n.
So,
Yes.
Okay, I'm good. Hmm. Okay, cool.
And then we can go down to figures five and six as well. Or I think the
Oh, wow. Okay. This one's got some lot to it. Okay. Eject-
yeah. So these
Ejection.
are sort of heat plots with the ejection time and the ejection velocity.
Okay.
Uh, so it's sort of hard to make out on the in the left pane when you see overall times and velocities. But when we zoom into sort of those the recent past, the past 10 million years in the right pane, we can
Hmm.
start to make out a bit more, and we can see where the majority of material, at
Okay.
what time it was being ejected, and what speed it was. And that's when we see with the brown square there that the majority is in about a million years ago in the past, but then also under 2 kilometers per second for ejection velocity. But then we do also get a lot of particles after the 1 million years past, closer to the the closest approach of Alpha Centauri and the Sun,
Yes.
and there tend to be the faster ejections because you can catch more of those particles as they're being released from Alpha Centauri.
Yeah. Very good. Nice heat plot. Okay. Hmm. All right. Onwards.
And then we have a similar plot below um, with this heat plot type look, but we do the travel time of the particles
Okay.
and the travel distance.
Yes.
Um, so this shows how long the particles were in sort of the interstellar medium outside of both the systems, but in the galactic potential. And then the relative travel distance is how far it travels relative to Alpha Centauri. So that helps us with one of the equations for how large a particle might be to survive.
Okay.
We need to know how far it travels relative to other particles to see. This helps with the what is a sputtering effect of grain-grain collisions that
Yeah,
they might.
exactly. Yes, yes.
Well,
Uh-huh.
and then we can see there that the majority of them, just like we saw before, where they ejected in the relatively recent past, traveled for a relatively short amount of time in the interstellar medium,
Hmm.
and therefore traveled a shorter distance because the distance between Alpha Centauri and the Sun was smaller at that time as well.
Good. That all ties together quite nicely. Okay. And there's some of our histograms of those apparent velocities.
Yes, yeah. So this is the apparent velocities I mentioned earlier with the how fast these particles are moving as they were approaching the sun. So these are their relative speeds at the time of their closest approach to the solar system. And we can see that they're pretty similar to what the actual Alpha Centauri system itself is, and that's because it was the relatively sort of slow ejection velocities that resulted in the close approaches.
Hmm.
And so most of them, the median value was about 32 and a half kilometers per second relative to the solar system. And that is that value that helped give us the heliocentric speeds once pulled into the inner solar system.
Yes, right. Equation 4. Okay. Awesome. Then 8 we covered. That was our radiance. And
Yeah.
9 was our global Mullenweed. Very cool. Okay. Ooh. Okay. So do we have any here with us in here now?
Yes, actually, yeah. So that is the interesting part. I'm not sure, Paul, if you want to talk a little bit, or if you want
Yeah,
to.
sure. Well, why don't I jump in for a little bit here? So yeah, so the question is, could any particles actually make it, and how many would we expect? So I think Cole has made the case that the particles have a dynamical pathway,
Yep.
uh, and we can make some arguments about the size of particle that could survive based on studies of the ISM and things like that. But to estimate the number of particles that might be in the solar system right now, we need some estimate of the number of particles that are being released from Alpha Centauri. And this is a number which is not very tightly constrained at all.
Yeah.
Really don't know what's going on inside the system. We know there's probably planets and there's certainly multiple stars. So the approach we took was to use our own solar system as a proxy for that,
Fair
because
enough.
some similarities between our solar system and the stars and Alpha Centauri. And so the best we can do is estimate the rate at which our own solar system is ejecting material and use that as an order of magnitude
Right.
estimate for Alpha Centauri. So the solar system ejects material in a number of ways, but maybe the best constraint is the loss of comets through planetary perturbations, essentially. So occasionally a planet will, primarily Jupiter, will slingshot a comet onto an unbound orbit. And so that leaves our solar system.
Uh-huh.
And so in section 4.2 there, we try to estimate the rate at which our own solar system is ejecting material and then translate that into an ejection rate for Alpha Centauri.
I'm with you.
So all the details are there, and there have been some nice studies of cometary detection rates in our own solar system that we lean on heavily there.
Yep.
But once you do the math, it turns out that there are probably thousands of particles being ejected from Alpha Centauri every year, and some fraction from Cole's simulations will be entering our solar system. And so at typical asteroid sizes, say 100 meters, kilometer sizes, or so forth,
Okay.
might be getting tens of those particles coming into our Oort cloud per year. And given the amount of time it takes them to transit through the Oort cloud, there might be 1 million Alpha Centauri originating asteroids and or comets within the Oort cloud right now, which is kind of an exciting number, though.
That it is.
We do have to be a little bit careful though, because the Oort cloud, of course, is very big, and we can't sample it very well telescopically.
Yes.
You can probably only see the volume, say within Saturn's orbit, about 10 AU, really well. Despite the advances in small body surveys and things like that, which are really pushing those frontiers. It's just hard to see these small faint objects, and so
Yes.
probably only a 1 in a million chance that there is an asteroid from Alpha Centauri within that 10 AU volume centered on the sun. So as many particles as there might be out there in the solar system, the odds of us actually catching one in the near future telescopically is quite small. So that's a little bit unfortunate, but it's still kind of exciting that they're out there. We just have to find them. So that's kind of on us, right? They're there, hopefully. But that's at larger sizes. So at smaller sizes, maybe I'll kick it back to Cole here. So there is a possibility maybe of seeing some of those too.
Yeah.
Yes, yeah. So
Stuff.
for smaller sizes first, and I don't want to jump back too far again, but if you actually just go to the beginning of the discussion,
Sure.
there
No problem.
is when we first start talking about the motion of these smaller objects. So we talked about how long they spend in the ISM
Uh-huh.
and their velocities that they have. So we can look at some great work by Norm Murray et al. 2004 paper. They look
Mhm.
at these effects that these bodies experience in the ISM. So that's from magnetic fields, the drag, which could perturb the direction of motion of these particles, and then sputtering by high speed gas atoms or grains hitting each other and decreasing in size.
Yes.
So looking at these three sort of effects and our motions of the close approach bodies that we observed actually leave Alpha Centauri and arrive at the solar system, we can make an estimate for the survivable sizes of particles. So that is what we did. We looked at the three equations that the Murray paper has and some values that they suggest. And we get that the minimum particle sizes that would survive is between about 1 and 73 microns. And the median of that is about 3 microns. So it actually was applicable to very small grains when it comes to the survivability of these particles that travel from Alpha Centauri to the solar system. Now, of course, 3 microns in size is extremely small and would be very difficult to detect. So because of that, when we're doing some of this analysis for ones we might observe as a meteor at the Earth, we have to use some larger sizes. So we adopt about 100 microns in size for a meteor that you might be able to observe in Earth's atmosphere.
Okay. Okay.
Yeah. So with that 100 microns, that's when we can jump back into our number and flux estimates in 4.2. Down on the next page. And after taking the same sort of idea that Paul already mentioned with the larger bodies, we can sort of apply that to some smaller bodies, but to try and extend, the model for the number of asteroid-sized bodies down to micron-sized bodies is extremely difficult. So we try and do it with masses instead. So we take that lower end with about 100 meters in size from the asteroid size model and distribution. We convert 100-meter objects to a kilogram mass, and then we figure out how many 100 micron size particles might be in that mass.
Yes.
So if we do that, some calculations here, which don't need to cover too much. We use it's a bit further down on this page here.
It's all good. Take your time.
Yeah.
Here we go.
This little formula here. When we do all this and we figure out how many particles might be in that mass, and then we also now look at the relative cross-section of the Earth compared to the solar system, which of course is very, very small in comparison. It's hitting a very tiny moving target. We get about 8 meteors from Alpha Centauri might enter Earth's atmosphere per year.
Okay.
And that's about an upper limit based off of those estimates that we make. But it's non-zero, which is super interesting. This could happen. So that is a very interesting part. We could actually be having Alpha Centauri material that is intersecting Earth's atmosphere, maybe a handful every year. And these numbers are actually expected to increase with time. As we saw, when Alpha Centauri is closest to the solar system, we get our largest number of close approaches that occurs. So we expect these numbers that both Paul and I mentioned to increase by about a factor of 10 in about 28,000 years when the systems are closest to one another. So if we were to look at that, maybe we'll get about 100 meteors per year in 28,000 years. And if we want to compare that to actual solar system meteors,
what's the relative?
It's a very small fraction. It's a very, very small fraction. So we talk a little bit about Seymour, which is the Canadian Meteor Orbit Radar at Western here in London. And a paper from there suggests that after, I think it was 6.8 years, the top right of this page, they make an estimate for how many meteoroids might be intersecting the Earth per year from solar system bodies, and it's about 7 trillion. So in comparison, we get about 1 in a trillion meteors might be from Alpha Centauri. So there's our estimate for just how rare these events actually would be.
Or even by astronomical standards.
Yes, yeah.
Well, it's kind of like it's maybe kind of there's might be an analogy with gravitational waves in the past, or
Yeah.
Yes.
or
Yeah.
or, or neutrino detections coming up, this kind of
Yeah,
things.
yeah.
Yeah,
Yeah.
well worth taking a look at. So very cool.
Rare, but possible. I think that's the interesting part.
There you go. There, but don't get your hopes up. But
Yeah.
it's
Yeah.
there. Very cool. Very cool. Cole and Paul, I want to thank you so much for walking us through your very thought-provoking article on material from Alpha Centauri. Very nice.
You're very welcome.
Yeah, I appreciate the interest in it as well.
Sure. And you kind of touched on it a couple of times there as we went on through. Uh, and so I'm curious, where do we go from here given the published article? Is there more sophisticated in-body simulations to do? Might there be some observational signatures on light curves or things of that nature? So just sort of next steps. Where do you think we go from here given the published article?
Well, for the Alpha Sen case, I think the interesting thing is now we have some values to sort of expect from Alpha Sen material.
Okay.
So that might help link if any other interstellar material is discovered, which it surely will be with some larger surveys and with just time for meteor detections. So fingers crossed I might see one, and hopefully we'll be able to link it back now because of some of these values that we provided. And then moving forward in sort of a bigger picture, we'd like to sort of extend what we've done here to some other star systems as well. Perhaps ones that are ejecting maybe a higher amount of mass into the galactic potential. So ones that might have larger mass reservoirs, say in disks, debris disks, protoplanetary disks.
Maybe
Um,
Bernard Star. Maybe Bernard Star.
yes, yeah.
Maybe, yeah, yeah.
Yeah.
Yeah, it's
So
very exciting. We've got, I mean, we have found a few interstellars, of course, and we're going to find more, especially as Cole mentioned with LSST Rubin coming online.
Yes. Yes.
Just we're gonna find these things, but we really want to understand where they're coming from. Maybe try to get a little bit ahead of the curve here in our understanding of how this material travels through the galaxy. So lots of possibilities out there.
Always good to have predictions instead of post-it. Yeah.
Yeah.
yes.
Very cool. Very nice. Cole, Paul, thank you so much for walking us through your very awesome PSJ article. I appreciate it.
Thank you, Frank. Yeah.
Yes, thank you.
And that'll do, everyone. And I hope this made your astronomy, your interstellar astronomy day just a little bit better. And we will see you on the next one. Bye-bye.